artificial intelligence. We objectively assess the importance of this topic. However, there is still no consensus on whether all tasks can be solved using these technologies. Abuse or obligatory use. We will raise such issues of ethics, modern information society, and cybernetics. This is the story of our virtual conference on pattern recognition and information processing in 2021, which has already begun. Here, right now.
So, dear colleagues, I would like to invite you to our last scientific session of the conference. I hope you already enjoyed with our trailer video, which actually reflects 30 years of history of our conference. And now we will come to the first presentation of the last sessions. Well, last doesn't mean least. Yep. So I'm giving the floor to a speaker of the first presentation, Enhancement of Land Cover Classification by Training Samples Clustering. Please, you have a floor.
Hello, dear colleagues. Can you hear me?
Yes. Yes.
Just one moment. Can you see my presentation?
Yeah, just make it visible in a full screen mode. Yeah, thank you.
My name is Artem Andreiev, and the name of presentation is Enhancement of Land Cover Classification by Training Samples Clustering. As it's known, land cover classification is still challenging in heterogeneous landscapes. The problem arises from the mixing of land cover classes and their training samples. The solution of the problem is seen in the application of hybrid classification models based on combining both supervised and unsupervised learning. This study aims to enhance land cover classification accuracy by clustering of training samples to decrease its mixing. The potential of the proposed approach is explored by mapping the natural landscapes of the Tsviatkou Natural Park. Here you can see the algorithm of proposed hybrid approach to classification. Input data contains satellite image and training samples for each class. Training sample set should satisfy such requirements as completeness, sufficiency, and purity. The main idea is clustering of training samples. It is performed to decrease training samples mixing, and it is performed separately for each class by supervised classification. So as you can see, the subdivided training sample set contains subclasses of each initial class. And after that, obtained training sample set could be applied for the classification of input image. And to create final classification, the subclasses should be merged into initial classes. And if you're talking about training samples mixing and its unmixing, there should be the criterion of its mixing. I propose to name it a separability index of training samples. This index quantifies the separability of training samples. Calculation of separability index is similar to the standard calculation of classification overall accuracy. And it equals to the ratio of correctly classified training samples to the total number of training samples. On the right side, you can see a little example. There are two classes, and each class has 5 training samples. But after classification, there are only 8 correctly classified training samples. Each class has 4 correctly classified training samples, as you can see here. So that's why the separability index equals to 0.8. It means that there are 80% of correctly classified training samples. And here you can see the algorithm to identification the most appropriate combination of subclasses. This algorithm iterates over all possible combinations of subclasses and calculates the separability index for each combination. And then combination which reaches the highest value of separability index among other combinations would be the most appropriate combination of subclasses. Also, I have developed 2 software modules. First of them is to calculate the separability index of training samples and to provide the most appropriate number of subclasses for each class. And the second software module is for clustering of training samples and classification of image. There are 5 types of unsupervised classification and 3 types of supervised classification. Also, this software module displays the result, and of course, the result could be saved. And a few words about experiment. The study area was Shatsky National Park. It is Volyn region, Ukraine. And satellite image for the study area is Sentinel-2. Field data contains about 100 georeference sample plots providing ground truth information about the representative landscapes of the study area. And as you can see, there are 6 land cover classes. Artificial surfaces, forest, natural grassland, agricultural areas, water bodies, and inland wetlands. The result of this experiment. Initial classification was obtained by application of Mikhailov's distance classifier as the method of supervised classification. And spreadability index of trained samples was 91%, and overall accuracy of classification was 77%. And after application of proposed approach, by using K-means as a method of unsupervised classification, the spreadability index was increased by 8%. And overall accuracy was increased by 4%. Here you can see 2 land cover maps. And as it was mentioned, overall accuracy was increased just by 4%, but there are 2 classes which accuracies were increased significantly. The class number 1 is artificial surfaces, and as you can see, the producer accuracy of this class was increased by 45%, and user accuracy was increased by 17%. Also, there is class inlet wetlands, and its producer accuracy was increased by 27%, and user accuracy was increased by 10%. Here you can see the differences between 2 land cover maps, and especially you can see differences between 2 classes, artificial surfaces and inland wetlands class. And conclusion. What was developed and presented? Criterion of trained sample separability and blind approach to enhance classification accuracy by decreasing trained samples mixing, and 2 software models. And I think that further research should be aimed at developing new separability indices and optimization of developed software models. That's all. Thank you for your attention. I hope you have some questions.
Okay, thank you for your fast, rapid, and clear presentation. Dear colleagues, please ask questions if you have. I see none. I'd like to ask you just one question. 6 classes. Why 6? Can we come back to the classification? Yep.
Yes. Because initially we had some georeference samples. Yes, we just had this a priori had this data, and that's why there are 6 classes. It is very global class, not a local class. I mean, they're big, very heterogeneous, and that's why I wanted exactly those classes. Because they're mixed, they're heterogeneous. Okay, have you tested other, let's say, vendors? I mean, not Sentinel multispectral, Sentinel-2, but other type of satellites? Yes, of course. I even tested on the SAR, I mean, Sentinel-1, and even on the other optical images like Landsat, and the result was good. The result was good. Yes. Same 6 classes. Yep. What? The same 6 classes. No, not only 6 classes. Could be 10 classes, 5 classes. Okay. So, but this number is just just. It's just for example, just for this example, just for this study area. Okay. Thank you. Thank you. Any other questions?
Can I ask you?
Yes.
My question is, why do you not use the so-called graphical models to process image in pictures in image analysis?
I'm sorry, could you repeat the question, please?
Why you didn't use so-called graphical models to process images? This is a well-known technique which is very effective. And for the classification and for comments, we need to use special enhancement of this algorithm to combine different classes. But the graphical model, graph models, is a very well-known technique to process complex images with multiple classes. Why you didn't use it?
I just wanted to develop my own search module, yes, and because I wanted to apply it to the train samples, unsupervised classification, as you can see. And
this is a technique with the train samples and so on.
Understood. You mean another technique? Yes.
Technique.
Another technique.
Well-known developed technique, graphical models.
Graphical models?
Yes, of course.
What do you mean graphical models? Graphicals like GUI or graphical unit, or what do you mean?
Okay, thank you very much.
Okay, sorry, maybe I didn't understand.
Yes, yes.
That's okay, thank you. Any other questions? So I see none. Okay, we move on to the next presentation, which will be given by Ahmedkhan Radzhabov, I guess. Performance analysis of deep learning models for herd segmentation and chest X-ray images on a small data set. You have a floor now.
Hello, can you hear me?
Yes.
Yeah. Thank you for giving time. My presentation is about the work that I did in sake of solving some problems of my main work. It's the name of the title of this work. I mean, of this exact work is performance analysis of deep learning models for herd segmentation and chest X-ray images by X-ray image and small data set. Actually, I didn't mention, my supervisor is Vasily Kovalyov, and I'm working in the laboratory of biomedical image analysis, and it's part of the biomedical image analysis group. So main purpose of this work is recognizing extrapulmonary abnormals on chest X-rays. It's the main purpose of this thing is to solve some problems in recognition of abnormalities in image like this. I mean, this X-rays provided by some medical institutions like from Belarusian state. Can translate it pulmonology, I think, institutions. Okay, and next, understanding the influence of network parameters on the quality and performance of segmentation. And next one is augmenting of the data set through automatic segmentation. The last one is like one of main things, because there's not so much of segmented masked images in the open source. So we have something like just hundreds of masked images for this work, and we have not masked like that big data set without any masks millions of photos, and there are like hundreds, thousands of images of like X-ray images of X-rays with illnesses related to heart disease. Main attention in this work made for heart abnormalities as cardiomegalia. It's this disease when heart is bigger than it should be. Here we can see that this illness is somehow distinguished by images, not so good in some cases, but in general we can see differences. So we can solve it by this automatical processes, because they use kind of close to our retinal recognition patterns. So let's speak about this segmentation part. There are some existing solutions, and there's three of them. It's from US Institute. They did the chest X-ray data set, and they had something like let's say championship on like a recognition of this image, and they have some results. And one of them is like best one is shown here. It's performance of this segmentation model, and other one is decathlon. It's other place to compete. It's like competition, and there was some good results here either. And here we can see some like how some of them worked. First one is like same X-rays, but others is 3D CT images. So it's a little bit different approach, but still we can use both ways to solve it. And here's data set. It's masks, and there is image, and we can see that they reply to each other. And also I have this big data set provided by medical institutions from Belarus, and it contains some data, text data in databases, explanations of disease of these images, find it on these images. And there's a small data set. It's 100 images for masked images. And I used the resolution 512 on 512 because it gives more performance than 256 on 256, but maybe in future I will choose second one, because it's for bigger data sets, it's more useful. It performed on NVIDIA RTX 2070, and it's proceeds for from 1 to 30 minutes per run. So this is like results. I think I have not so much time to explain, but first result you can see it worked. It's for region of interest with resolution 96 on 96, and it gives this bad result, but it's just find that this parts wasn't the hard, and so we can use maybe this approach in different tasks. And by increasing region of interest, we approach to better result, and then we use cropping of image, and then we get this result with good masks, visually good masks, and actually good biometrics. You can see there are some kind of problems with this spots on these masks, but it could be easily solved by basic algorithms of relating this part by choosing like biggest part on image. So it's performance results, and on the left hand it's for low region of interest, and on the right side it's for balanced region of interest. And here's the results compared on different like runs, and so you can see it by increasing region of interest, we increased performance and I mean quality of recognition, and this gives us some results. And so I will use this for future for improving of main algorithm of recognition of heart disease, and there was some problems with this data sets, because there was like in huge data set we have had some say shifts. I mean, the data wasn't selected in the best way, because there I was missed some points. I mean, because of like sorting of this data based on time, it was some problems, and this part of problems was find out because of work of Vitaly Levchuk, and I want to thank him for working on with this data set and for providing some code and etc. Thanks for your attention.
Thank you for your presentation. Please, now we have time for questions. I see none. Well, I would like just comment that yes, previously we listened to the presentation of Vasily Kovalyov and asked him about different application of this small data set neural network approach, and now we have different kind of application. I mean, different images, different kind of images. So of course, it highly depends on how distributed this data set. Yes.
Mm-hmm. Yeah.
Okay. Thank you.
It's very important. Thank you for comment.
If you'd like comment me or something else, you may currently.
I think you're right. Yeah, it's very important to have a good data set and like balanced one, and sometimes it's hard to find this balance in a work, because sometimes there aren't any signs of disbalance of this data, and it could be found in in random place, and maybe didn't even found till the end.
It's quite important. And you mentioned decathlon. I mean hackathon. So you participated in a competition worldwide, yes?
I didn't participate, but some
that's your colleague.
Some colleagues from lab participated. And they have some results comparable to results with this work, and so I mentioned them because of this. They had better results because there was different aims, because mine was just to compare some types of nets and of parameters of them, and so because of this, performance of my work was much lower, but still there was the results on heart. This part is only about heart disease, so we can see there 3D net results, and I used UNet, so it's something like maximum maybe for my work.
Different nets, that's clear, that's understood, but were there any special rules for participation in that? I mean, special data set, because this approach is specially designed for small data sets, highly distributed data, or other type of rules? Do you know?
No, as far as I know, they have bigger data set than mine, and it is 3D data set. It's for CT images, and so because of type of this data set, because CT contains of many of layers, it's maybe a little different story, but as far as I know, they hadn't any. They had own data set, but they hadn't any restrictions based on size of.
That's clear. Thanks again for answering my questions. If we have other questions, just please unmute your microphone and ask. No, we have none. Well, let's go further to the next presentation, which will be presented by one of co-authors of the presentation entitled "An Automatic Pruning Method for Skeleton Images." So,
okay. Can you hear me?
Yes, we're clear.
Okay, I will share the screen. Wait a minute. Okay. Oh, can you see my Can you see my screen now?
Yes, now we see your screen. Thank you.
Okay. Okay. So let's start. The title of my presentation is "An Automatic Pruning Method for Skeleton Images." First, skeleton, also termed as medial axis, is an efficient and compact descriptor for pattern recognition. Skeletonization is a set of methods that extract the skeleton from the two-dimensional shapes or patterns while preserving topology of the original image. A fact that can limit the use of the skeleton in application is that the skeleton method may sensitive to small deformations along the object boundary. Even negligible boundary noise can cause spurious skeleton branches. So skeleton pruning techniques are very useful. Skeleton pruning methods are based on the use of criteria for the evaluation of the significance of skeleton branches to take a decision on whether to remove or keeping them. Clearly, branch removal caused by pruning method modifies the skeleton in such a way that the object represented by the pruned skeleton is characterized by a smooth boundary or a different number of protrusions compared to the original object. A pruning process is adequate if the resulting skeleton structure is noticeably simplified, but the above differences are negligible for the specific application. Look at the house in the right side. We can see that the top one has many spurious skeleton, but the bottom one is very clear, is very good, is very clean. Exciting pruning methods are all based on the silence measures of the significance of contour, segment, or skeleton branches to identify the noise branches. So the skeleton pruning can be seen as the task of seeking a suitable threshold, and this procedure needed interaction with the people for tuning. Here, we list some popular pruning methods, including pruning by contour partition with discrete curve evolution, pruning method with bending potential ratio, pruning algorithm based on information fusion, and pruning algorithm based on the silence sorting. Although these methods based on different criteria to remove the skeletal branches, they all need some parameters to tuning by the people. For example, the first method needs the stopper parameter K. However, this kind of manual tuning is tough and thankless job, especially when the input images come from a large data set. Where has many different shapes. So based on this motivation, we decided to develop an automatic pruning method. Since bias method is one of the most cited pruning methods, we decided to study how the stop parameter K influence the pruning result. Thus, we start to increase the K from 3 to 30. The 3 is the minimum value that used in their paper. And 30, I think, is a very large value. This also can be set as the total number of the branches in the initial skeleton. From the slide, it can be noticed that with the rising of the K, more skeleton branches are retained rather than removed by the pruning algorithm. And if we use the skeleton data resulted by the pruning method to conduct a reconstruction operation, we can observe that the reconstruction image may closer to the original image when we continuously increasing the stop parameter K. However, it is also apparent that the increment of the reconstruction area between two consecutive reconstructions is decreasing. So the main idea of the automatically selecting a proper parameter is derived from this. Here is our proposed method. It's a pursuit code. For our method, there are 3 inputs, which are original skeleton, which you extract from the binary image, and the silent points. This we can obtain by using the discrete curve evolution method, and our original binary image. And our output is the pruned skeleton. In the first step, we conduct the initialize. In the next step, we pair the endpoints in the skeleton with the nearest silent points. Then we sort these endpoints by the significance of the corresponding silent point from large to small. Then we take some top endpoints along with their skeleton branch to reconstruct the original image. Next, we will repeat this operation and we will repeat this operation until the consecutive two reconstruction area is not above a given value. In the end, we can output the final endpoints with their skeleton branches. In order to better analyze the performance of the proposed method, we compare the proposed method with the bias method. It is worth noting that the bias method is based on the skeleton that extracted by the skeleton growing algorithm, which is based on the distance transform, whereas the proposed method is based on the skeleton that extracted by the thinning method. So there are some difference between the results. And the test images are from the well-known benchmark Ahmedkhan 7. We can see that for this image, the bias method can generate a clean skeleton when the stopper parameter k is set to 3, and the middle image is the skeleton resulted by the thinning algorithm. And based on the middle image, the proposed method can also result enough clean result without any tuning parameters. For the next image, the stop parameter k of the bias method should ascend to the 15 to obtain a skeleton that maintain the original topology. If the k is above the 15, the bias method cannot preserve the topology of the original patterns, whereas the proposed method still can result a satisfying skeleton without any tuning. For this image, we can see that the bias method, the parameter of k of the bias method is shrunk to the 10. However, our method can automatically generate a good skeleton. Then we end to the conclusion. In the proposed method, manual tuning of the pruning parameter is not necessary, which is inevitable in many pruning algorithms. Therefore, the proposed method is more convenient to use than others pruning method. In the future, it is interesting to test our method in a larger dataset and conduct a statistics to prove the priority of our method. Thank you for your attention. If you have any question, please ask.
Okay, thank you for your presentation. Now time for questions from colleagues.
Hello. Thank you for your presentation, but I have asked about pruning because as far as I know, algorithm of pruning shouldn't have any parameter for stopped.
Right.
But in your report, I don't see any condition for stopping algorithm. You show your slide again and showing me this path.
Okay. Here, because we use this parameter to stop when the area this means the correct construction area. If we have a pruned skeleton, we use this skeleton to reconstruct try to reconstruct the original pattern. If it has above this value, we all at the area. We need to think about the two consecutive area reconstruct difference. We see the difference and the area they covered. So that's the step parameter. It depends on all the data set to find this number and this number.
Thank you. It's clear. Thank you.
Yeah. Thank you for your answer. That is quite clear. Any other questions? I see none. So now we move on. I think we have to jump over the next presentation since we have one speaker from the presentation 6.4. Have we? No, we haven't. Okay, the last presentation, which will be given for us by Alexander Labocha, Artem Shamina, and Alexei Ardako. Sorry for my pronunciation now. Quite difficult to pronounce. Even surnames are quite clear, but in spelling no. Well, cloud detection in aerospace imagery of environmental monitoring. So any of co-author, please. Now you have a floor. So seems that we have. Your microphone is muted now. Yeah. If I'm not sure who is the author. Please type a message to chat if you're author of the last presentation, because you're muted. Please unmute yourself, or we should conclude. Seems that this is the end, actually. So I'm not sure that we have a speaker from the last presentation. Okay, well, now colleagues, just to conclude epically our conference, because we have 4 days conference, so it's quite a big time that we engaged of you. I hope you spend it well. Now, let's move on with our trailer and intro, and then come back. Please do not disconnect for our closing session. Thank you.